Hello everyone, my name is Cheng Shen, currently a PhD student at Peking University. In this talk, I will introduce our paper, When LoRa meets EMR, Electromagnetic Covert Channels Can Be Super Resilient. This is a joint work with Tian Liu, Dr. Rui Tan, and my PhD advisor, Dr. Jun Huang. EM covert channel is a classic data exfiltration attack, where the attacker steals classified data from a computer by using a malware to manipulate the EMR of memory, power management unit, USB, and so on. Conventional covert channels hide data in network traffic, thus relying on a compromised network interface. In contrast, EM covert channels exploit the infiltrated computer as a radio transmitter and thus can bypass a variety of network security measures, such as firewalls, traffic monitors, and even air gaps, where network interface cards are disabled or removed to physically isolate classified data from the outside world. However, due to the low power of EMR, the threat of existing EM covert channels has been limited to only short-range attacking scenarios. For example, prior studies show that the EMR of a typical CPU memory system can be decoded within only 5 meters, which demands the attacker to be unrealistically close to the target system. In addition to path loss, covert EM signals are subject to the attenuation caused by shielding. For example, the Tempest standard developed by NATO and the National Security Agency requires classified systems to be shielded by a minimum of 1000 decibels. In comparison, the EMR of a typical CPU memory systems is only 15 decibels above the noise floor. In this paper, we challenge the common belief that EM covert channels are vulnerable to attenuations caused by path loss and shielding. In particular, we ask if EM covert channels can survive deep attenuation, thereby achieving long-range or breaching aggressive shield previously considered as secure. To this end, we revisit EM covert channels with LoRa, a state-of-the-art wireless technology that enables kilometer-level connectivity for energy-starved IoTs. LoRa features an attenuation-resistant modulation called chirp spread spectrum. In each chirp, signal frequency linearly increases with time, leading to a pattern that can be distinguished from significant noise. In LoRa, different bits are represented by different cyclic shifts of chirps. For example, the right figure shows 4 chirps, each carrying 2 bits represented by one of 4 possible shifts. Motivated by the super resilience of LoRa networks, we ask the question, is it feasible to exploit EM sources as LoRa radios to fundamentally escalate EM covert channel attacks? To explore this feasibility, we design, implement, and evaluate EM LoRa, the first EM covert channel that can exfiltrate data over long distance and aggressive shield. We conduct extensive experiments to study the performance of EM LoRa and demonstrate how EM LoRa enables attacks in previously impossible scenarios. The key idea of EM LoRa is to exploit memory as a LoRa radio transmitter. EM LoRa shares the same attack model with previous EM covert channels, but can significantly boost attenuation resilience by 5 orders. To achieve this, EM LoRa faces several unique challenges. From a signal processing angle, EM LoRa must handle the complex spectrum of memory EMR. From a system angle, the malware of EM LoRa faces uncontrollable CPU contentions, which pose a fundamental challenge for precisely shaping covert signals. In the following, we demonstrate how attackers can circumvent these challenges to make EM LoRa feasible and reliable. EM LoRa's transmitter is a user space malware that shapes memory EMR by manipulating memory writes. The code of EM LoRa transmitter consists of 2 parts. The first part is a fixed frequency EMR generator, which alternately writes 2 equal-sized byte blocks into memory because the 2 byte blocks produce different current flow patterns in memory bus. The generated EMR approximates a square wave, where byte block size determines frequency. To generate EM chirps, a naive method is to call square wave with a linearly increasing frequency. Unfortunately, the chirp energy generated in this way is very low because of CPU contention, which makes EM LoRa unable to accurately control the timing of generated waves, thus introducing frequency errors. To address this problem, EM LoRa performs approximate chirp generation. Specifically, it first divides a continuous chirp into discrete frequency levels and then generates multiple square waves at each frequency level for a certain dwell time. Because square waves at each frequency level are independently affected by timing errors, the average of their frequencies follows normal distribution, according to the central limit zero. The variance of average frequencies decreases as the number of square waves increases, which means that the longer the dwell time, the stronger the EMR energy at the intended frequency. Based on empirical observation, we found that the dwell time of 1.5 milliseconds is sufficiently robust to generate strong chirps. To decode the covert signal of EM LoRa, it's important to understand the spectrum characteristics of memory EMR. Specifically, before chirp modulation, memory EMR is purely produced by memory clock, which is generated using spirit spectrum to reduce EMR intensity. As modeled in this equation, a memory clock is the sum of a series of subclocks. For example, the bottom figures show the EMR spectra of DDR3 and DDR4. Agreeing with the model, the energy of memory EMR is distributed as a series of peaks, where each peak corresponds to one subclock. We observe that the modulation of EM LoRa introduces complex features into the spectrum of memory clock. Specifically, chirp energy is dispersed as a series of mirror images, where each subclock is associated with an up chirp and a down chirp. In addition, each up and down chirp produce a sequence of harmonic images. Such energy dispersion significantly reduces the intensity of EM chirps, thus posing a key challenge to EM LoRa receiver. We have developed a theoretical model to explain such modulation impacts of EM LoRa on memory clock signals. Details of the model can be found in our paper. To decode covert EM chirps, EM LoRa augments the standard LoRa receiver to handle the complex spectrum of memory EMR and performs a series of signal processing to fuse the dispersed chirp energy to boost covert signal intensity. This figure shows the high-level signal processing pipeline of EM LoRa receiver. Specifically, it first performs symmetric dechirp, where it converts up and down chirps into fixed frequency signals. EM LoRa then sums the results of symmetric dechirp of fused energy of mirror chirps. To further fuse chirp images associated with subclocks, EM LoRa exploits the periodicity of subclocks and performs the folding, a fast signal processing algorithm originally used to amplify extremely weak periodic astronomical signals. After folding, dispersed chirp energies are fused into one energy peak, whose frequency indicates the bits carried by the chirp. As a user space malware, EM LoRa transmitter has to share the CPU with other processes. As illustrated in the figure, CPU contentions of other processes may block the malware transmitter of EM LoRa, which interrupts the transmission of covert signals and distorts the generated EM chirps. To further understand the impacts of CPU contention, we test the effect of different CPU loss on the frequency and the power of EM chirps. As shown in the right figure, EM chirps begin to suffer distortion when CPU becomes fully loaded. The frequency error and power loss of generated chirps further increase as the CPU becomes overloaded. To make EM LoRa survive CPU contention, we leverage the trade-off between throughput and chirp robustness. Specifically, longer chirps carrying fewer bits improve robustness but degrade throughput. In comparison, shorter chirps carrying more bits degrade robustness but increase throughput. Based on this observation, EM LoRa first estimates the level of CPU contention and adapts chirps to balance bitrate and robustness. Specifically, it first measured the timing error experienced by chirps and then uses the timing error as a feature to classify the level of CPU contention. Based on classification results, EM-LoRa switches between three predefined spread factors calibrated for underload, full-load, and overload, which define length and indicates the number of bits carried by each chirp. The right figure shows a runtime example of chirp. In the beginning, EM-LoRa transmits short chirps for higher throughput when the CPU is under load. When CPU load increases, EM-LoRa increases chirp length to improve robustness. We have implemented a prototype of EM-LoRa's receiver using BladeRF, an expensive software radio equipped with a 2.2 dBi whip antenna. The Malware transmitter is deployed on different systems equipped with DDR3 and DDR4 of different speeds. We compare EM-LoRa with GSMIME, a state-of-the-art memory covered channel. For fair comparison, both EM-LoRa and GSMIME are implemented using the same BladeRF receiver and then compared under the same bit rate. We observe that compared with GSMIME, EM-LoRa improves attenuation by up to 53 decibels and extends its communication range by up to 21 times. When receiving from the DDR3 desktop, EM-LoRa achieves a range of 2000 to 2050 meters and then resists up to 78 decibels attenuation. We note that the resilience of EM-LoRa can be further improved using high-gain LNA and directional antenna, which typically provide an additional gain of up to 70 decibels, and thus will allow EM-LoRa to defeat the 1000 decibels bar of Tempest. We then evaluate the performance of EM-LoRa under CPU contention. We studied two types of contending CPU workloads, including video streaming and Monero coin mining. This figure shows the good pulse of EM-LoRa as a function of attenuation when rate adoption is on and off. We observe that rate adoption effectively maintains attenuation resistance under CPU contention. Specifically, it prevents about 2 and 5 decibels gain over the basic EM-LoRa. Next, we demonstrate how EM-LoRa enables attacks in two previously impossible scenarios. By achieving long communication range, EM-LoRa enables wide area data exfiltration, which allows an attacker to deploy a receiver in a public area to receive classified data exfiltrated from a building. To demonstrate this attack, we use a DDR3 laptop as EM-LoRa transmitter and deploy it in a building with concrete walls. We then place 5 receivers at 30 and 1020 meters away from the building. We observe that all packets can be correctly decoded at R1, R4, and R5 due to long communication distance. Receivers at X2 and X3 experienced an moderate packet loss with a loss rate of 11.2% and 53.4% respectively. We further conduct retracing-based emulations in two scenarios, where we deployed EM-LoRa receivers in a public park and a sports center to receive covered signals leaked from two government buildings located in Washington, D.C. and Beijing. In each scenario, we place transmitters in 3 selected locations within the buildings. We found that in the DC scenario, the EM-LoRa receiver can decode most packets and limit packet loss rate at below 20%. In the Beijing scenario, EM-LoRa suffers a relatively high packet loss only when receiving from TX2 at X2. We found that this is caused by the block of a building that cuts off the direct path between transmitter and receiver. We next demonstrate through the wall data exfiltration from an aggressively shielded server in an indoor area. The target server is deployed in room D and is shielded by a commodity Faraday cage that prevents about 70 decibels attenuation. We observe that without shielding of Faraday cage, leaked data can be received at all locations except A. When the target server is enclosed in the Faraday cage, location B and I turn to dead spots. Despite that, EM-LoRa can maintain a bitrate higher than 2 bps at all other locations. In conclusion, we presented EM-LoRa, the first super resilient EM covered channel. EM-LoRa exploits memory as a covered LoRa radio. It shares the same attack model with prior EM cover channels, but can significantly boost attenuation resilience by up to 53 decibels. By achieving this, EM LoRa can enable attacks in previously impossible scenarios, including wide area data exfiltration and Faraday cage penetration. In the future, we plan to further investigate the implication of EM LoRa for other EM sources and develop effective detectors and countermeasures to mitigate EM LoRa's threat. Thanks for listening. Please direct questions related to this work to the following emails.